Okay, let's go. Key Computer Science Unit 1, May, June 2021. This exam actually happened in July, but close enough. So let's start. Question number 1. Draw the symbols for each of the 3 basic logic gates. Just draw the symbols. Alright, cool. So we have the NOT gate. We have the OR gate. And we have the AND gate. Alright, those are the symbols. You should get 1 mark for each. Nothing too special there. Did they ask you to name it? We should name it. Not, or, and. They didn't ask you to name it, but I'm positive that they will give you a mark. But they won't give you a mark if you don't name it. Draw the associated truth table for it. So let's go. Not is 0 or 1. You have a not gate have a not gate, just have a X, and then you have the output. The output will be 1 or 0. OR gates will be, you have a X and you have a Y. You have, usually your inputs will be 0 0 0 1 1 0 and 1 1, right? You're basically counting from 1 to 3 in binary usually. And then you have the output. So 0 and 0 will give you 0, 1 or 1, 0, 1 or 0, 1. Once you have a 1 anywhere inside our OR gate, you'll get output as 1. And you have an X and you have a Y, and you have it out. Of course, 0 0 0 1 1 0 and 1 1. That's what you're basically going with there. Always the same inputs. 0 and 0 give you 0, 0 and 1. So only 1 and 1 will give you 1 in our AND gate, right? That is that. Each one of those is how much marks? 3 marks. It's kind of strange, eh? Like drawing a diagram and labeling it is 3 marks, and then doing a whole truth table for it is 3 marks also, 1 mark for each. But hey, we're taking it. Okay, draw the truth table that shows the output for NOT, X and Y. Right, so when you start with this, you always go to X and Y, start off with that, and then from the X and Y, go into what the inputs will be, 0 0 0 1 1 0 1 1. Let's go with the X and Y first, so X and Y. We put it through our AND gate, so that means it'll be 0 0 0 1. That's X and Y. And then you want to get not X and Y, so X and Y, and you could symbolize the not with a big line over the top of them, which is the opposite of whatever you have there, which will be 1 1 1 0. That's that there. 2 marks for that. Oh, they're real stingy with the marks in this paper, but interesting. Okay. Write the logic expression for a circuit that can provide the following truth table. Alright, so we have to do the sum of products, right? So sum of products means anything that gives you a 1, you want to or that, add them together. So we have addition definitely between 2 things, and we have a normal X and a not Y giving you a 1. So this is X and not Y on one side, and then the other side will be not X and normal and Y. So it's not X and Y plus X not Y. Basically what you're trying to show there. Yeah, sum of products. I say the range of integers with 8 bits using if you don't understand the sum of products things, you might want to check out some of the videos that I have, or check out the crash course where I explain these things in a little more in-depth views, because that usually gives students some trouble. Alright, so the range of integers with 8 bits using sign and magnitude representation. Alright, so your highest possible value with sign and magnitude is if you have 1, 1, 1, 1, that means this here is the sign. So that means the best that you can get there is -7. And then if you have 0, 1, 1, 1, the best that you could get will be, oh no, it's 8 bits. My bad. I'm very sorry. It's 8 bits. So we had to go 1, 1, 1, 1, 1, 1, 1. Right. So you get -127. And then on the other side of the spectrum, you will get +127. Right, because remember the bits, the first bit is the sign bit. So you gotta treat these two first bits here as sign bits, or else they won't be included in the calculation. They won't be included in the calculation, basically. Alright, the binary sequence, blah, 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 equates to the decimal value 126 using 2's complement. Show the steps involved in determining the 8-bit 2's complement representation of the value -126. In the binary sequence. In the binary sequence? I mean, if the binary sequence? I don't know. What do you mean, man? Show the steps involved in determining that the 8-bit 2's complement representation of the value 126 in the binary sequence is... Alright, basically we want to do 2's complement, right? So we're going to start by inverting the bits. So they gave us the bits already, which is 126. So we'll invert. And you'll get 1, 0, 0, 0, 0, 0, 0, 1, and then you have to add 1. When you add 1, you'll end up getting 1, 1 is 0, carry 1, so that'll carry that 1 then, and I get 0, 0, 0, 0, 0, 1, which matches back to that. Alright, so as you mark there, should be good. Yeah. You invert and add 1 here. Explain what happens when a computer uses 8 bits 2's complement integers. Attempts to evaluate the expression -126 - 3. To explain that, okay, basically what you want to say for 5 marks is that it will basically do, it will add -3 to -126. So you're basically going to get -3 plus -126. That's how it will add it. Then you had to convert the 3 to 2's complement. The -3 will be 0, 0, 0, 0, 0, 0, 1, 1. You invert that, you'll get 1, 1, 1, 1, 1, 1, 0, 0. You add 1, you'll end up getting 1, 1, 1, 1, 1, 1, 0, 1. Right, good. So when we get our 1, 1, 1, 1, 1, 0, 1, now you're going to do the addition. So we have to do the binary addition. So we basically have to show 1, 1, 1, 1, 1, 1, 0, 1 plus -126, which you just got, which is 1, 0, 0, 0, 0, 0, 1, 0. Right? Now that we have those two, we could do binary addition for it. Actually, it'll be easier if I put them on each other one time and add them, because they say show all working, so I'm going to show all working. So let's go 1, 0, 0, 0, 0, 0, 1, 0. Right, so we go and add this now. 1, 0 is 1, 0 and 1 is 1, 0 and 1 is 1, 0 and 1 is 1, 1 and 0 is 1, 1 and 0 is 1, 1 0 is 1, 1 and 1 is 0, and then you get 1 here. So this is the carry 1. So yeah, basically that's what you get. How are they breaking this up into 5 marks? I guess you would get 2 marks for doing the 2's complement from -3, knowing that you have to add it to the -126 as 1, then add in here and getting the carry 1. Yeah, that should be 5 marks then. That is worth 5 marks. Alright, write the decimal value that is represented by the sequence. Alright, Alright, sequence is 1 0 1 1 0 1 0 1. Alright, so they tell us that we have a 1-bit sign, so this is the sign. 4-bit mantissa, so this is the 4 bits for the mantissa here, and then a 3-bit exponent. Alright, so let's go. This is sine, this is mantissa, this is exponent. Alright, so we go in with the following context. exp is 1 0 1, which is essentially 0 1 2, which is 2 plus 1, which is 3. No, exponent is not 3, exponent is 5, my bad, because this is going to be 1 2 and 4, right? So 4 plus 1, exponent is 5, right? So if we know that the exponent is 5, then we could solve, well, we could get the mantissa now to be 0 1 1 0, and we want to go 5. Oh, that's plenty to jump by. Alright, so let's do the jumping. We jump in 1 2 3 4 5. So in essence, what we're going to get would be 0 1 1 0 0. And now we have to convert that to a decimal number, which will be 1 2 4 8 8 and 4 is 12, so we should get 12. And because the sign was negative, it'll be like negative 12. It's not even a decimal, it's basically just a number. So negative 12 is the answer. Now, there is a problem that they could have here. I think they could have a problem because normally when you have a number, the first one is the sign, next part is the exponent, and this part is the mantissa. So I'll solve it for both of them because I believe that it's possible that they made a mistake here. Because not all question, like there is no... Yeah, I feel they mix us up by the way that they say it, because it's supposed to say 1-bit sign, then 3-bit exponent, then 4-bit mantissa. If that's the case, then it will be like this. It'll have 1 0 1 1 and then 0 1 0 1, which is how I kind of wrote it in the first part. So you have 1 for the sign, this for that, that for that, and then I would give you a mantissa exponent of 3 because it's 0 1 1 1. Which will be 3, and then you take the 0 1 0 1, and then you move the point 1 2 3, which will give you 1 0.1, and our 1 0.1 is basically 2.5, and because the sign is 1, it's negative 2.5. I am convinced that this is what they were intending to do, because it's very weird for you to get a decimal value and then turn out to 12. That's not normal. Yeah, so I'm convinced that's what they want to do. If you see a question like this, I believe that they would have to cater for the way that they stated the question, where they said 1-bit sign, 4-bit mantissa, and 3-bit exponent. If you followed that pattern, then you should be okay. But normally, anytime you have to do any questions with decimals and binary, there's always have the sign bit, then the exponent, then the mantissa, which is the second way that I did it, right? So that's how you get decimal number. Alright, number, okay, page 9 is blank. Okay. 2. Flip-flops and registers are commonly used by computer systems. Say the meaning of the term flip-flop. For 1 mark, what they usually want is a circuit or bistable device that stores 1 bit, essentially like that. Bistable device that stores 1 bit. Draw a label diagram that depicts how a set of flip-flops can be used to create a 4-bit register. I find this question there's plenty, right? But what you kind of want to show is you want to show the concept as a flip-flop is a box that has an output called Q, right? And each one of these Qs will be able to store a bit of information based on the output that you get here. So essentially what you're going to have is like you're going to have like 1, 0, 0, 1, something like that. This is how they actually store information inside of a register. But there are 2 inputs to the flip-flop that you need to take into consideration, and they would usually have a input. And each one of them will have their own input. And each one of them will have their own input, but that input will be based on another input that you're going to have, which is usually the clock signal. So I'll kind of pull this out here, and each one of them will have to be connected to a clock. CLK. Right. So the clock signal, when it goes into the flip-flop, depending on the input that you give it, will give you a particular output. So you'll get like if you want to have a store the number, this is what, 8, the number 9, 8, yeah, 1, 2, 4, 8, yeah. This is storing the actual number 9 inside the register. So flip-flops, when you put them together, they have an input and they have a clock signal, and they give you an output of Q. And Q is usually where the output goes. So you kind of need to know how to put them together. The most important part here is the clock signal, because the clock signal is going to determine how it changes. This is how I like you add numbers. So usually you'll like 0, 0, 0, 0, then you'll have 0, 0, 0, 1, 0, 0, 1, 0, and it will keep adding up like that. That's how flip-flops work. Alright, say the name of the smallest addressable unit of memory in RAM in a modern computer system. Unit of memory. That will be a byte. It can't be a bit. No, yeah, because you'll have to send information to or pull information from the memory by using a byte, right? A byte, yeah. Write the name of the circuit most commonly used to achieve the following objectives. Select a specific memory location given a memory address. Ooh, this is tough. A specific location given a memory address. If you get a memory address, it will choose a particular location. When you get a memory address, it will be 8 bits that coming in. And those 8 bits will have, I will want to say, a decoder. A decoder is used to select memory addresses, yeah. Select one input from multiple inputs, that is definitely a multiplexer. Yeah, definitely a multiplexer. I'm not 100% sure about the C part 1 with the decoder, but it sounds like it's decoder. But like when they apply it to a memory address, I'm not too sure what they mean, but a decoder will always choose one location, but there are many locations it could choose. So yeah. State the purpose of virtual memory in a computer system. Well, I promise you 100% this is not supposed to be on Unit 1 syllabus. So I heard from reliable sources inside the CSEC machine, the CXC machine, that they didn't mark this question. They didn't give marks for it. So this is only for Unit 2 children. But you know, the explanation is, I'll put it still. It provides a fake location or fake size of RAM to make the computer store more temporary information. Alright, basically it's a fake size of RAM, virtual memory, meaning it doesn't exist, right? The three components of the virtual memory system, well, they're wicked, eh? But the whole question wasn't marked. So you have physical RAM, you have the hard disk drive, and then you have the page file. Alright, so the page file will keep track of the information of the locations of each one of them, and then you keep swapping them between the physical RAM and the hard drive. But again, as I said, that's Unit 2 stuff. What again describe the interaction between components of a computer system that allows virtual memory access to be accessed? Alright, you want to say when memory needs to be accessed. How much marks is this? 3 marks? Alright. The CPU references the page file, and the page file points, no, page file swaps the value from the hard drive to the physical RAM for use. And the table is updated. File is updated. Yeah, basically the CPU wants something. It is told swaps the value from the address drive and the page file is updated. Yeah, essentially that. So basically, if it can't find it in the hard drive, it will swap it into the if it can't find it in the main memory, then it will swap it from the hard drive and put it in the main memory physically. Yeah, but our whole question there was not answered, so our whole 7 marks was basically given to every student this year. State the 3 main components of the CPU. Inside the CPU you have the ALU, you have the CU, and you have registers. Nothing else inside there. Everybody just falls in line with those guys. Describe the role played by each of the components stated in E during the instruction cycle. Alright, 6 marks. So you want to say that you're talking about the instruction cycle, so that's the fetch execute cycle. Fetch, decode, execute, right? So let's go piece by piece. Fetch. The CU fetches the instruction from memory and decodes the opcode and operands. Yeah. Then you want to say the fetch, decode, fetch and decode. Execute now. The ALU performs the mathematical calculations and stores the results in the appropriate register. That's sounding good there? I believe so. Yeah. 6 marks. 2, 4, 6 each one, yeah. Yeah, 2 for the fetch part, fetch the instruction. Next 2 for decode it, decode the operands and whatnot. ALU performs mathematical calculations and then you store it in your registers. Yeah. Right. It's cool, yeah. Alright, that's module 1. Alright, it's that time of the year again where it's time for crash courses, because you spent your whole year fighting up with school, not being able to go to school when you want to, always worrying about COVID, all kind of issues. So I have all the CSEC IT, CAPE IT and CAPE Computer Science crash courses that you need. I'll be able to give you the whole syllabus in one quick dose to be able to get you over the hump. So here's how the crash courses will be going this year. So for all the crash courses, we have 3 different levels that you could choose from this year. Level 1 is video only. That's just a video that'll be about 6 to 8 hours long that covers the entire syllabus, going through in a kind of like a speed run, explaining every single thing, but not explaining every single thing, if you understand what I mean. Level 2 is a video and a class in April where you get to ask me anything about the syllabus. So you'll get the video in advance, you could watch it about 2 to 3 days before, and then you come to that class and then you ask whatever question you need to ask. And the third one is you get the video, you get that class, and you get access to our WhatsApp group directly to be able to ask me questions at any point in time whenever you're doing any past paper, whenever you're studying any work. And that's how the crash course is going to run this year. So the crash courses will be CSEC IT, CAPE IT Unit 1, CAPE IT Unit 2, CAPE Computer Science Unit 1, and CAPE Computer Science Unit 2. Those are the days. Each one runs from 9 to 12. That's if you take the class option. You will be able to come into that class and ask any question about the syllabus, and of course you will get the video a few days in advance where you could watch through the whole thing. So what are the costs? Well, for all crash courses, CSEC and CAPE, Basic, which is the video alone, will be $150. $200 will be for the standard, and the Pro will be $250, which is the video, the class, and the WhatsApp group to ask questions at any point in time. So how do you register? You have to makeITsimpleTT.com/crash course, and you will be able to see all the courses that are available. You choose the one you want, you register, go through the payment, and then you will be given the video. Once you're given the video, you will be able to watch it at any point in time. Of course, if you register for the other ones, you'll be given the video and you'll be given the timetable of when your class is going to be. You'll be added to a Google Classroom. And if it's a Pro, you'll be given the video, you'll be given the class, and your phone number will be added to our WhatsApp group. So that's makeITsimpleTT crash courses. So I look forward to seeing you all. April, everything is going to be launched, so you can register from now, which is from March, for them. And you might just get the video before the end of March. And just in case you're wondering, these crash courses cover the new syllabuses. So the new syllabus for IT CSEC that launched a few years ago, the new syllabus for CAPE IT, and the new syllabus for ComSci. All the new stuff, all the things that they put into the syllabus that may not be always clearly explained, or the current textbooks don't have it, these crash courses have it. makeITsimpleTT.com/crash course. So I'll see you all there.